Hi, so today we're going to talk about electron configuration, and we're going to focus our attention on the smaller atoms from hydrogen, helium, lithium, beryllium, and that's where we're going to stop. And then in a subsequent video we'll talk about the larger atoms, more complex atoms. So the first question that we must answer always is, what's our motivation? What's the big deal about electron configuration? Well, an electron configuration is important to us because this tells us in which orbitals the electrons reside. Remember, we're not fixing their physical locations. We can't do that, but we are saying, okay, this electron is in this orbital, okay, in this general region, let's say. And once we understand where the electrons are, it helps us understand the reactivity of these elements. Okay, it helps us understand these elements' reactivity. It also might help us understand their proclivity towards attracting extra electrons, so their electron affinity. And other physical properties like the size of an atom. So this might help us understand or start to see things like, is this atom going to be very large, very small, and that kind of thing. But considering that elements engage in chemical reactions in order to change around their electron configurations, understanding the electron configuration of an atom is very important. It's also very important as we talk about electron configuration to realize that we are talking about what's called the ground state. The ground state electron configuration. And so realize that just as a boulder might roll down this hill until it reaches the lowest potential energy resting place, an electron too will go towards the orbital which has the lowest energy. And so that's kind of the lowest potential energy resting place for that electron. That's not to say that you can't subsequently push the boulder back up the hill, acquiring some input of energy, right? So it's also not to say that you can't later take that electron and excite it to another orbital, a higher energy orbital later. But all we're going to talk about today is the ground state electron configuration of these elements. You also should remember that in a previous lecture or previous video, we talked about the different orbitals that these electrons could reside in. One possibility was the 1s, and then here comes the 2s, the 2p, the 3s, the 3p, and so on and so on. We won't list them all out. That'd take forever. All right, and theoretically they go on forever. All right, but all we're saying here is that if you're hydrogen, let's say you're a hydrogen atom and you don't have an electron, so you're an H+, and you acquire an electron, right? So here you are, you're H+, and you get an electron. Where is that electron going to go? Well, the electron is going to go all the way into the lowest potential energy orbital, and this is going to be the 1s. All right, so now you're hydrogen, and you have an electron that's residing in the 1s orbital. So we can describe the electron configuration of this hydrogen atom in a couple of ways. Okay. So the first thing we'll say about the hydrogen is that its electron configuration is 1s1, meaning that it has one electron in the 1s orbital. The other thing that sometimes you'll see is people use a box diagram. So we'll let this box represent the 1s orbital, and we'll let this upward facing arrow represent that electron. Now, from this description here, we can get the quantum numbers of this electron. Okay, so remember that this 1 right here has reference to the n value. So this tells us right away n equals 1. This letter right here, the green, I'll underline in green, this tells us the L value. L equals 0. Right? We know from our quantum numbers that if L equals 0, then M sub L also must equal 0. No other choice. And then when we look at this upward facing arrow, this tells us that m sub s is equal to plus 1/2. So this is the quantum numbers that describe the location of this electron. All right. Now, let's say we wanted to add a second electron to hydrogen. We wanted to make hydride, or you wanted to add a second electron to your system. Let's say you're talking about a helium atom. We can't use these quantum numbers. We've already used these quantum numbers to describe the location of an electron. So if we wanted to add a second electron to this system, we can't use that set of quantum numbers. We've already used this. The Pauli Exclusion Principle, I'll write his name over here, says that you cannot use this set of quantum numbers again. We've already used this set of quantum numbers to describe this first electron. The second electron, we have to come up with a set of different quantum numbers. So for the second electron that we're going to add now to make, let's say, helium, we're going to put this also in the 1s orbital. And you say, wait a minute, you can't put that electron in that orbital. You already used it. Well, look at this. I have two possibilities for m sub s, remember? Spin up and spin down. So here the 1s orbital has a spin up electron and has a spin down electron. So, hearkening back to the 1 here, this tells us that n is equal to 1. Okay. The s tells us that L is equal to 0. The m sub L must be equal to 0. If we have an s orbital, it's always equal to 0. And now that we have a spin down electron here, the m sub s is equal to minus 1/2. And so in this way, both of these electrons have their own set of quantum numbers, but we can't use this set again. So basically what this tells us is that when we go to add our third electron to form lithium, there's no more room in the 1s orbital because there's not another set of quantum numbers that would follow the rules and be unique. So as we go now to talk about lithium, okay, we remember back to our order that we had a moment ago on the slide, which was the orbitals were going to increase from 1s to 2s, 2p, 3s, and so on and so on. Well, what we've just done with hydrogen and helium is we have filled up the 1s orbital. There's no more room in the 1s orbital. So if you want to write the electron configuration of lithium, fine. It's 1s2. That describes the location of the first two electrons. The third electron is going to have to go in the next orbital over. So it's going to go 2s1. So that describes the location of 3 electrons. All right. So, what are the quantum numbers that describe this electron? Well, if you have to, go to the box notation. Here's the 2s. Here's your upward facing electron. Okay, spin up. So, n equals, all right, 2. L equals 0 because it's an s orbital. M sub L equals 0. M sub S is equal to plus 1/2. All right. Now, when we go next door to beryllium, fine. Now we'll add that second electron in the 2s orbital. So for beryllium, okay, we're going to go 1s2. That tells us we're the first 2 electrons. Okay, we had 2s1 for lithium, 2s2 now, because we just added an electron on. So what we're doing is we're just building the electron configuration of beryllium based upon the electron configuration of hydrogen, helium, and lithium. Okay, we're building up these electron configurations. This is what is meant by the Aufbau Principle. Okay, Aufbau for building up. Okay, so let's talk about the quantum address of this last electron that we added, meaning the, for our 1s Here, remember we had spin up, spin down. For our 2s, this was our third electron for lithium. The fourth electron, this is the one we want to talk about now. Describe the quantum numbers that go with this electron over here. So what is it? Well, remember this is the 2s orbital. So n is equal to 2, L is equal to 0, m sub L is equal to 0, and m sub s is equal to minus 1/2. This electron is spin down. Well, what we've just done as we've gone from hydrogen to helium to lithium to beryllium is we've gone along and added more electrons to our system, and we filled up some orbitals as we've gone. Remember the electron configuration here, 1s1, and here 1s2. Here was 1s2, 2s1, and for beryllium it was 1s2, 2s2. So if you're noticing here, we've now filled up the 1s orbital and the 2s orbital, and in our next video we'll talk about what happens after that when we start filling the 2p. Alright, so just to give you a quick overview of what we've done today, we talked about the ground state electron configuration of 4 elements, hydrogen, helium, lithium, beryllium. We talked about the Aufbau Principle, which meant we just built upon the previous electron configuration. And we spent a lot of time determining the quantum address of those electrons that we're adding to these elements. And we said that due to the Pauli Exclusion Principle, we cannot use that set of 4 quantum numbers twice. So once we've used a quantum number set, we can no longer use it anymore. And basically what that's done for us is said that we can put a maximum of 2 electrons in each orbital. Alright, well thanks for watching, and I hope you have a good day.